Hello, welcome to section 7.1, example 1, where we're going to be talking about exponential functions. In this example, we're going to have an exponential function, here's one, and we're going to figure out if it shows growth or decay, and then we're going to try our best to graph it. And if you watched the previous video, if you went through all 30 minutes of it, then everything for this one should be easy. The only difference is that this number is a little weird, but I want to show you how to get around that. Okay? So the first thing I want to figure out is, do I have exponential growth or decay? Well, let's go back. Here's the sheet that I had at the beginning. What's the base of my exponent? The exponent is the variable x. What's my base? My base is 1.5. If that number is bigger than 1, I have exponential growth. 1.5 is bigger than 1, so that's true. It's growth. But if it was between 0 and 1, then I have exponential decay. So, since 1.5 is bigger than 1, this means that I have exponential growth. And my graph should look, it won't exactly look like this one, but it should look like this and not this one. My second example is going to look like the other one. Okay, so how do I graph it? Right? Well, the best way to start is by making a table. And unlike my previous video, I didn't set myself up with a table here. So I'm just going to pick some x and y values. And let's just say we can go from -6 to 6 if we need to. Exponential growth explodes. If it's growth, it's going to go up this way. So I probably am not going to get very far. Let's pick some, and I need some negative numbers here too. So let's say -3, -2, -1, 0, 1, 2, 3. And if I need more, I can come up with more. This is just a place to start. All right, so what did I say where to start first? Start where x equals 0. 1.5 to the 0 power equals 1. Any number, except for 0, to the 0 power equals 1. And my scale here is different than the last video, so 0, 1 is right here, because notice there's 2, 3, 4, 5, 6. So I got that. Okay, well now what's 1.5 to the first power? Well, that's going to be 1.5. Super. So if I come over here to x equals 1, I go up to 1.5, which is right here. All right, cool. Now, here's where, yeah, go ahead. You can do it. Grab one of these. But you don't need to. You guys are in accelerated algebra. You can do it in your head. Why? Because it's easy. I'm going to write it up here. 1.5 is the same as 3 over 2. Why in the world would I want to change it to a fraction? Because 3 over 2 squared means 3 times 3 over 2 times 2 equals 9 over 4. Now, if you want to keep it as a decimal, you can. Just take 9 divided by 4. You would have already been using a calculator anyway, but that's okay. You can do 9 over 4 in your head. Or, since I'm graphing it, it's kind of hard to graph improper fractions, and I hate calling them improper. But you can change it to a mixed number. You can say this is 2 and 1/4. If you get a calculator, it'd be like 2.25. And if I did 3 over 2 to the third power, that's 3 times 3 times 3, which is 27. 2 times 2 times 2, which is 8. And 27 divided by 8 is going to be 3 and 3/8. So, and if you change it to a decimal, that'd be 3.325, 375. All right, so where's that going to be? Let's see. Oh, you know what? I think I messed up. Sorry, ignore this one. I was going by 2's. Whoops, you didn't see that, okay? And if I had some white out, I would change this. This is actually supposed to be right here, because I was at 2 and 2 1/4. Oh, wait, I'm sorry. I'm getting confused. That one's correct, this one's wrong. 2 1/4 is right about here. Whoops. And then 3, which is here, and 3/8 Here's 3, and 3/8 is going to be about right there. Okay, so part of my graph is going to look like this. I got disoriented on my graph. This is why you should never use markers. Okay? So I can keep this up. I can now try 4. That's going to be 3 times 3 times 3 times 3, which is 81 over 16. And yeah, you can kind of figure out, eventually you're probably going to need to use one of these. Okay? So, and you can do it in different ways. That was where I was last time. Second quit. So I can do 1.5 to the 4th power. And that's the same as 81 divided by 16. Right? Either way. It's just arithmetic, guys. I don't care how you come up with it. Right? So that's just going to be a little bit bigger than 5. So 4 is going to be a little bit bigger than 5, which is about right here. And it looks like my graph is going to start to curve up this way. I might want to figure out what 5 is. It's probably in here someplace. That's okay. For the negative x's, it's going to be the reciprocal of all these. That's where using the fraction is very, very important. Because what's the reciprocal of 1.5? Well, I don't know. But what's the reciprocal of 3 over 2? That's 2/3. What's the reciprocal of 9 over 4? That's 4/9. And what's the reciprocal of 27 over 8? That'd be 8 over 27. And notice that these are getting smaller. So it goes from 1 to 2/3, which is about right here. Then it goes to 4/9, which is a little bit less than half, which is about right there. And then it goes to 8/27, which is about 1/3, which is about right here. And then, like we said in the last video, it never touches the x-axis because this never equals 0. And on this side, it never goes perfectly vertical. It's very, very steep, but it never goes perfectly vertical. So, in my mind, yeah, you can grab a calculator here. Okay, so let's do y equals, clear that out, and I'll do 1.5 to the power of x. And let's make a table. So there's my table. I was already on the negatives from the last example. But here's the numbers that I have. 0 gives 1. 1, let's go up. 1 gives 1.5. This is 2.25 and 3.375, etc. Okay, great. And of course we get 2/3, which is 0.6 repeating. 4/9 is 0.4 repeating. And then 8 over 27 is, it's kind of hard for me to see, 0.2963, and that does end up repeating, but they only show four decimal places. Okay? So, and then, yeah, go ahead and graph it. You can graph it. Looks like that. Shows a little bit more over here than we would, but that's basically what I have there. Okay, but what's cool is that now you can do this yourself. You don't need to rely on the technology. I'll pick up the speed with the next one. Now this one has something different. It has that 30. What in the world is that going to mean? Okay, so let's make my table. Still keeping with the vertical. X. Let's say we'll do -3, -2, -1, 0, 1, 2, 3 again. And if I need more, like I did last time, I can include them. Let's start with 0. 0.8 to the 0 power equals 1. But don't write 1, because after you take care of the exponent, you have to multiply. So 1 times 30 equals 30. So, this is an example where I have a function a times b to the x power, which I talked about in the first video. Sometimes I take my exponential part, the base, the b, to the power of x, and then I multiply the whole thing by another number, by a coefficient. In this case, I'm multiplying by 30. That has powerful applications in finances, but we'll get to that. So where do I graph it? When x equals 0, y equals 30, which is right here. Now the next one is going to be I mean, certainly you can grab this, but let's see if we can talk about it first, okay? I need some space here. I'm gonna have 0.8 to the first power. Well, we know that that's I know that that's 0.8. And then I'm gonna multiply that by 30. But you know what's gonna make this actually easier to do, believe it or not? I really believe people wanna stop talking about, they stop talking about fractions and they do decimals just because they grab a calculator. I want you to do this in your head. This is the same, 0.8 is the same as 4 over 5. See? So if I raise that to the first power, I get 4 over 5. And if I multiply it by 30, I can think of it this way. I can do 30 times 4 and get 120, and then 120 divided by 5. Or, since multiplying and dividing happen at the same time, I can do 30 divided by 5, which is 6, and 6 times 4 equals 24. So this is going to give me 24. And let's see where that graph is. Here's x equals 1, and I go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, right here. So it looks like my graph, I'll draw part of it right like that. The next one is going to be 30 times 4 over 5 to the second power. That's the same as 30 times 4 over 5 times 4 over 5. Okay, I already know that this is 12. Oh, I don't know why I said 12. I already know this is 24, okay? I've got to double it. So if I think, I got some room here. If I think 24 times 4 over 5, now 24 divided by 5 is it's not gonna work, not like last time. So I can do this. I can do 24 times 4 divided by 5, which is gonna give me 19.2, right? So again, I'm doing a mix of fractions that you can do in your head, and also sometimes a calculator does come in handy. I'm giving you options. 19.2 is going to be about right here. So this is going to keep doing like this. All right. So anyway, if I do 0.8 to the third power, and then I multiply that by 30, I get 15.36. And to the fourth power, 0.8 to the fourth power times 30, I get 12.288. And I certainly don't need it to be that accurate. I'm not going to be able to draw it that accurate. So let's do it all at once. 30 times 0.8 to the power of x. I should probably use parentheses. If it doesn't work, it's because I didn't use parentheses. Let's do my table. 0 gives 30, 24, 19.2, 15.36, 12.288, 9.8-ish, and let's do one more. 6 is going to be about 7.86, maybe 7.9 if I round it up. So where am I at? So 4, oh darn, I forgot that I was, dang it. Okay, I'm gonna call an audible real quick. I'm gonna pretend that that's a 5, and that that's a 10, and that's a 15. Okay, you never saw that. So now I am going by 1, 2, 3. So 2 was about 19.2. 3, which is right here. I'll make my mark so I don't lose track. 3 is about 15 and a little bit more, which is about right here. 4 is a little bit above 12. And 5 is, did we say 9.8? Make sure I copy that right. 5, yeah, okay. So about right there. And it looks like my graph, I may not have everything perfect here. It looks like it's going to go that way. So I can keep picking bigger numbers here and graph this. Eventually this is going to curve this way, but it never touches, hopefully you guys are going to remember that. And it never equals 0. And then what happened on this side? Let's try this. -1, I got 37.5. So -1, here's 32, 34, 36, 37.5 is going to be somewhere up here. So it's going to go that way. So this is an example, I should have said this at the beginning. This is an example of exponential decay. Why? Because 0.8, the base of the exponent, is less than 1. It's also greater than 0, and it wouldn't make sense if it was negative. Okay, so it's not going to be 0 or less than 0. So I can just say because it's less than 1. Okay, we'll see you in the next video.